Yeah, so my name is Sky Hedden. I work at Kansas State University, but a lot of my research is focused out west. So today I'm going to be talking about the San Juan River. But before I get started, there's a lot of people, my co-authors, and a lot of individuals from different state, federal, and tribal entities that I want to thank because it's been truly a collaborative project. And so, like I said, I'm going to be talking about the San Juan River. We have a highly imperiled native fish community, and what's receiving a lot of blame to our lack of recovery of our native fish is this introduced channel catfish population. And so this perception that non-natives are bad is pretty wide across the world in the United States because there's a lot of evidence suggesting non-natives cause harm. And so because of this, the Department of Interior spends a lot of money trying to prevent or control non-natives. And in addition to a lot of money being spent, we spend a lot of time trying to eradicate or reduce non-native fish populations. So this figure here is just the number of channel catfish that have been removed from the San Juan River over the last 2 decades. And so what we see is, in recent decades, we're removing tens of thousands of catfish. And so this requires a lot of effort and intensive labor of going down the river and removing these fish. So not only do we spend a lot of time, but we spend a lot of money trying to eradicate populations. But despite all this time and money we spend trying to answer questions like what is the predatory impact of some of our non-natives, and more specifically, how many natives do our non-natives consume, we often lack this information. And so for my talk today and the project we've been working on for the past couple of years is really trying to address these 2 questions. So the San Juan River, it flows throughout the southwestern part of the United States over the Four Corners area. It's a sandbed river with an average discharge of about 2,000 CFS. And so within our main stem, we have 5 native species that live there, and 2 of which are endangered, 2 of which we've seen declining populations, and the last we really just lack information on. So we have this highly imperiled fish community, and like I said, what's receiving most of the blame for the impairment of these fish are our introduced catfish population. And so within this river alone, they're spending close to $1 million trying to eradicate the species without much success other than altering the size structure. And so we're trying to determine the predatory impact of channel catfish. And so it's a relatively simple question to ask, but it requires a lot of data to get reliable estimates. So in order to determine the impact of a non-native, what we really need is we need to understand the daily food intake of an individual catfish, and then also the probability of that catfish eating another fish species. And we need to know this across a wide range of environmental conditions. And so the 2 major components you really need to know this is the temperature evacuation rate. So how long does it take for prey to digest in the stomach of a fish? This gives you an idea of how quickly how quickly the fish will need to eat again. So you're going to need this at a wide range of temperatures. And then we also want to know the quantity of food that is being consumed and how this varies temporally. In addition to this information, what we need is you need a lot of information on the diet. How does the diet vary seasonally and year to year? And if there's any shifts in diet as fish get older. And then once you finally have all this information, you're going to need information on the population level, such as population estimates, biomass structure, and size structure, to really scale it up and to understand the total number of fish consumed. So once you finally have all this information, you can calculate or get an estimate for the total fish consumed. But then you're going to, of course, need to know the incidence of each of your native fish in the diet. And then finally, you get to the step where you can actually calculate how many of each of our native fish are being consumed. So this is kind of be the outline of my talk today. I'm going to go through how we've collected data at each one of these steps to finally get to this estimate of native fish consumption by our channel catfish population. So first, the temperature evacuation rates. So what we did is we held channel catfish in the lab at a wide range of temperatures of temperatures that are commonly experienced by fish in the wild. And so what we needed to know is, first off, if a catfish ate, and we need to know how much food the catfish ate. So what we did was we pit tagged fathead minnows and put them in the tank with the fish. And so what we were trying to do is basically just track the digestion rate through time. So we remove a subset of fish out of the tank and then see how much of that food is still in their stomach. And so with having our prey pit tagged, we knew exactly which catfish ate and how much food that catfish ate. And so when we look at, we can basically map out the digestion through time. So here on X we have hours. On a Y we have the proportion of prey or fathead minnows remaining in the stomach through time. So a value of 0 would represent everything you ate, you digested and passed. A value of 1 indicates everything you ate is still in your stomach. And so at our coldest temperature, we see it takes about 160 hours for catfish to pass or digest fish. And then as we increase the temperatures, this rate increases, which should be no surprise, until our warmest temperature, what we saw, it took about 25 hours for a fish to digest food. Okay, so now we have that step. We know the temperature-dependent rate of digestion, so this gives us an idea of how frequently our catfish are feeding at different temperatures. But now we need to know a lot about the diet. So what we did is we did bi-monthly sampling in 2018 and 2019 across about 150-kilometer reach of the river. So we had field crews going out, catching as many catfish as possible. So over the course of 2 years, we had almost 5,000 stomach samples collected. And so once we catch the fish with a raft-mounted electrofisher, so we just float down the river. And then once we catch a fish, we did lavage the fish into a seine or a sieve. And then so we're clear, I'm only going to be talking about fish over 300 millimeters. So these are our age 3+ fish. So once we have our stomach contents from the fish, we take it back to the lab, look under a dissecting scope, we identify the prey, sort the prey, count the prey, and then we also weigh the prey. So for each stomach, we actually have a dry weight of prey that was in the stomach. So now we have how the diets or how much food varies across different seasons and from year to year. So now we can calculate the daily food intake of an individual. In addition to all those diet samples, we also have a lot of data on now seasonal differences in diet, how diet differed among year, of course, environmental conditions, and then how diets changed with size. So with all that information, we can calculate the probability of a catfish consuming a fish prey. So we were trying to model what determines how much food a catfish eats and if they have a fish prey in their diet. So we can look at several environmental conditions that we think might be driving how much food you eat or if you're eating fish. And so looking at discharge in the system, we had a high variation from year to year. Temperature, there's the strong seasonality in water temperature, hotter during the summer, cooler during the winter. And then also turbidity. So this is a highly turbid system. We frequently have clear water, or infrequently have clear water, and typically we see these spikes in turbidity depending on rainfall. And so what we do is we can do multiple linear or logistic regression, and then we're going to rank our environmental conditions or abiotic factors to see which one's driving, first off, how much food the catfish is eating, and if they're eating fish. We'll rank all these with AIC. So first now, trying to understand the food intake of channel catfish. What drives how much a catfish eats? And so this is all food types. So primarily what with catfish we're eating were terrestrial seeds, aquatic plants, vertebrates, fish, and then some rare things like rabbits and rats you find in the diet. And so when we rank our environmental conditions or factors, what we see is this temperature-only model is the top model. We're simply here on our y-axis, we have stomach fullness, which is basically a metric of how much food is in your stomach, and temperature was the main driver. So at cold temperatures, they eat less food. At warm temperatures, they eat more food. It makes perfect sense. But now, what's driving fish consumption? So that previous graph was all food combined. Now we're trying to identify we're trying to predict the probability of you having a fish in your stomach. And so when we rank all of our abiotic factors, we also include total length in the model. So do larger fish eat more prey? So that's that TL there. So our top model is this turbidity and total length. So here on a vertical axis is the probability of having a fish prey in your stomach from 1 to 0 or 0 to 1. And so what we see is the fish were more likely to be in channel catfish stomachs with increasing turbidity. So as water becomes more turbid, we have an increase in fish in the diet, and with increasing catfish total length. And so when we have a large catfish in turbid water, they almost always have a fish prey in their stomach. But small fish in clear water rarely have fish in their stomach. And so now we have this information on daily food intake and the probability of catfish having fish prey in their stomach. So we can take this and now model up to our population level. And so luckily, the channel catfish are highly studied in the San Juan River. So we have yearly population estimates of channel catfish. So within this 150-kilometer reach, we have about 42,000 channel catfish that are greater than 300 millimeters. And we also know the biomass distribution along with catfish lengths. So what we see is most of our catfish in the river are between 350 and 400 millimeters in terms of biomass. So now we have all of our population information we need. So now we're ready to calculate the total fish consumed by our channel catfish population. And so here on the y-axis we have fish prey consumed. So this is in wet weight in terms of kilograms per river kilometer. And then here on our X, we just have time from 2008 all the way through 2019. And so what you see here is these obviously clear relationships with season. So during the warmer summer months, we see this increase in fish consumption, goes low again during the winter, and it increases again in 2019. But some things you might see is 2018 is a lot higher. So on average, we're getting 23.1 kilograms of fish consumed per river kilometer by our catfish population. And then in 2019, that number is much lower. And so what you see is there's a lot of these high values in 2018. In fact, almost half of the consumption in 2018 occurred about 40 days during the summer. And so when we look at these days, what's going on is these are warm summer days in which water turbidity increased a lot. So the probability of fish eating, and what we saw in the diets is when these warm summer days occurred, we see a lot of fish in our diets. So that's what was really driving the differences between year. So now we have an idea of how much fish is consumed by our population, but now we want to know the incidence of our different native species, because obviously they're going to be eating different natives, or most likely in different proportions. And so what we did was through our diet data, we could actually calculate the proportion of fish consumed, that's on our y-axis here, and then our different species on our x. And so what we saw is about half of the diet was made up by our native fish species, these four fish species here, including the endangered Colorado pike minnow. And on the non-native side of things, the most common fish were themselves. They were eating other channel catfish. And so now we have this incidence of each of our prey types. So we can finally calculate the number of our native fish species consumed by our channel catfish population. So of the 42,000 catfish in this 150 kilometer reach, what we see is for our bluehead suckers, they're consuming 200 to 500 of bluehead suckers per river kilometer. Our speckled dace, probably the most abundant fish in the river, they're consuming 1,000 to 3,000, depending on the year, and turbidity, of course. Flannelmouth sucker, again, 200 to 400. And then our Colorado pike minnow, our endangered fish, much lower numbers, probably because they're very rare in the river. But so now we basically were able to answer these questions by providing estimates to how many natives are consumed. So this is really a critical first step to understanding the impacts our natives are having on our native fish community. But now, importantly, what's our next step? How can we use this information to manage our non-native fish population? And so probably the biggest take-home or the most important information we gathered from this project was this relationship with having fish in your channel catfish diet. And so what we found out is, like I said before, increased turbidity, they eat more fish, and with increasing size, they eat more fish. And so in terms of management, there's not much we can do to manage the turbidity levels in the river, but what we can do is through non-native removal, which has been going on within the system, we can alter the size structure. So the interesting thing, what we found out is most of our fish of our adult fish are between 300 and 400 millimeters. So they make up almost half of the biomass of catfish in the river, but they only consume about 25% of our native fish. Interesting, these larger fish, so fish greater than 500 millimeters, make up a relatively small proportion of our biomass, 15%, but they're contributing much more to native fish consumption, almost consuming a third of our native fish. So if we can have non-native efforts that are targeting these larger fish, we can have more bang for our buck by reducing native fish consumption, by removing larger fish from the system. In addition to non-native removal, we can start with the data we can start looking at alternatives to non-native removal, mechanical removal, because that can oftentimes be very labor and costly, extensive. So with our data, we were actually also to show the reduction in consumption by channel catfish along a gradient of fish prey length. So basically, it should be no surprise, as fish get larger, you become less susceptible to being eaten. Well, with our data, we actually will look at that relationship. And so this is basically the reduction from 0 to 100% along a gradient of fish size. So what we see is fish less than 50 millimeters. Basically, the entire channel catfish can eat you. So, but as you get bigger, you become less susceptible to predation. And so this information is very valuable because with our endangered minnow, we have a stocking to try to enhance the population. And so currently our pike minnow stocking occurs at age 0 fish at 50 millimeters. And so what we found out is basically they're all susceptible to being eaten. But if we keep these fish in the hatchery for 1 more year, it is more costly, but what we see is there's about a 40% reduction in consumption by these hatchery fish that we keep in the hatchery for 1 more year. And so when we couple basically keeping our endangered fish in the hatchery for 1 more year, and if by continuing the ongoing non-native removal efforts, what we see is we can reduce the channel catfish consumption of our native fish, and primarily our endangered fish, by about 65%. And so that's all I have today. I'll gladly take any questions. Thanks for your time.